Good morning, everybody. Today is Friday, September 15th, 2023. This is the fifth lecture of the mini course on contraction theory at the University of Linkoping. And I would like to start today's lecture by briefly reviewing the last subject that we discussed yesterday, which was the contractivity theorem for interconnected systems. And I slightly changed the slides for clarity, so allow me to briefly review them. You have a network, and in this network, there are subsystems and lowercase n subsystems. Each of them has a state dimension. That's why in the picture, these boxes have different varying size. And I can introduce a norm in each of the subsystem, and I call these local norms, and I have lowercase n of them. And then in order to define a composite norm on the full space, I need an aggregating norm. That's a norm on just lowercase n. So you have capital N total state variables, but lowercase n. And then the theorem is that if you make the two standard assumptions to begin with that you would normally make, which is to say, assume that each individual subsystem is contracting and that the influence of the jth subsystem on the I subsystem is Lipschitz, as described by a Lipschitz constant Lij, then given those two assumptions, you can define an object called the gain matrix, like that, very, very simple, very natural definition. And then the third and final assumption is that this Metzler matrix is Hurwitz. And if this is if now all of these three assumptions, 1, 2, and 3, are satisfied, then you know a few things. You know that, well, this Metzler matrix is Hurwitz, so it does have a logarithmically optimal norm, or perhaps epsilon efficient. Let me not worry about that. Let's just call it logarithmically optimal for simplicity. That would be a norm in R lowercase n, because this matrix is only describing the interconnection, so it's not on the full space. So this norm you can use as an aggregated norm. From there, you define a composite norm on the full system, and that's the optimal norm. Well, that's the norm with respect to which the contraction rate is just equal to the spectral abscissa of the gain matrix gamma. So that's what we ended up. So it's a conservative condition, but it's oftentimes easy to check, and you immediately get a contraction rate out of it. There's a collection of, and I want to encourage you to be curious about the Hurwitzness property for Metzler matrices, and there's a lot of conditions and these various equivalent conditions for the Hurwitz property of a Metzler matrix. In fact, from there, you can easily extract the information that you need in order to define and compute the optimal norms that we have been discussing. All right. And the proof is rather quick and straightforward. Okay, so this is now a new slide. You have now an interconnection theorem, and you can use it in many ways. And in this slide, I am highlighting one possible ways to use it. People are interested in studying something called singular perturbation analysis. Imagine that you are dealt a problem like this, where you have a block matrix, and the first row is depending upon a parameter epsilon. How can you ensure that the matrix is Hurwitz? And it turns out that it is not. You can use that theorem that I just shown to you to establish that if and let's fix appropriate norms. I'm not going to discuss the norms. Let's say the norms are given. If the log norm of A is negative, the log norm of D is negative. So this is Hurwitz for sure. This is Hurwitz for sure. And then if I have a small gain condition, remember for a 2x2 Metzler matrix, the condition ends up being that the product of the diagonal terms in magnitude has to be larger than the product of the off-diagonal term, because on the diagonal terms, you have the contraction rates, which give you stability. On the off-diagonal terms, you have the Lipschitz constants that give you instability. So if you now ask, the two diagonal terms multiplied together to be larger than the two off-diagonal terms multiplied together. And notice that I am using log norms here and induced norms there. So this is the one-sided Lipschitz, and this is Lipschitz. Then what I can prove using the theorem that I've shown to you is that the block matrix is Hurwitz, and it is Hurwitz for all epsilon. By the way, notice that epsilon multiplies A and B. So if you come here, there's an epsilon on the left-hand side and an epsilon on the right-hand side, so they just simplify. So that's why the test here does not depend upon epsilon. All right, that's fine. This is not, this first row here is not singular perturbation. This is just a direct application of the theorem that we have seen to a block matrix. So here there are two subsystems. The first subsystem is described by epsilon A, the second is described by B, and so on and so forth. Now, on the other hand, in singular perturbation theory, people are interested in a different property. They're interested in saying, when is it true that there exists a sufficiently small epsilon such that the matrix is Hurwitz for small epsilons? So not for all epsilons, but only when epsilon is small. How do the conditions change? And it turns out that if you perform an appropriate change of coordinate and then apply the network contractivity theorem that we've seen earlier, then you get the conditions that D is Hurwitz, and the Schur complement, which is A minus B, D inverse C, is Hurwitz. So I can use the theorem to prove that this condition here, these two matrices are Hurwitz, implies the Hurwitzness of the block, the full system for sufficiently small epsilon. And I don't actually use singular perturbation theory. I do it using the network contraction theorem that I have just shown to you. And by the way, for those of you who have never had a chance to study this, what you are observing here is called a commutative diagram. So these properties imply the property on the right. They also imply the property on the bottom left. The property on the bottom left implies the property on the right, and top right implies the bottom right. Does that make sense? So it's nice to have this. Now, in contraction theory and in all of this field, as I have mentioned to you, everything is rather explicit. There are no anonymous constants such as epsilons and deltas and other things. It's all very explicit. And to confirm this one more time, I can give you this expression for the epsilon star. So in singular perturbation theory, you would say there exists an epsilon star such that when you are below it, good things happen. Oftentimes that epsilon star is hard to compute. In this particular case, I know this looks like it's a long expression. However, every single object is very clearly easily computable. These are induced norms and induced log norms of the various matrices that appear. All right, so this was one first application of the network contraction theorem. Allow me to show you another application. In the slide deck, at this point in time, I should show you more properties of contracting systems. So I'm going to skip these properties, but I'm going to come back to them later. I'll just show you some more examples where you can use this network contraction theorem. Let's just see how we can use it. So in modern engineering, of course, the importance of optimization is extremely high, but then also people are interested in games. People are interested in studying problems where there are 40 people and each one of us is pursuing our own private individual benefits, but then we are interacting. And the question is it true that the collective system, what is it doing? Does it find, if each of us pursues our own independent interests, is it true that there exists an equilibrium? And it's called the Nash equilibrium. And is it true that if I write down a natural dynamical system for how things change, is it true that the dynamical system converges to the equilibrium? Does that make sense? Any questions? So let me repeat it. In game theory, oftentimes the first question is, does a Nash equilibrium exist? And then can I write, does this dynamical system converge to the Nash equilibrium? Okay, but then isn't that a contraction theory question? Meaning to say, does an equilibrium exist? Well, then I'm just going to try to see if I can prove that certain dynamical systems that describe the game are contracting. Because if they are contracting, then the Nash equilibrium exists. It's unique, and the dynamical system that I am designing will converge geometrically or exponentially fast in discrete and continuous time, respectively. And on top of that, it will have all of these robustness properties, including the incremental ISS and so on and so forth that we've been discussing. But by the way, there is a special class of games which are called aggregative games, where what happens is that your interaction with all of the other agents arises through some aggregate quantities. For example, we all want to use electricity. The more people use electricity, the higher is the price of electricity, but the price is the same for everybody. So all of our actions affect the price of electricity. And so therefore your decision, your performance, your utility is affected by everybody else, but through just a single scalar quantity. So it's a special structure that I will study as well. All right, so let's start with the simplest problem that I can think of, which is called saddle dynamics or saddle gradient, in fact. All right, so this is called also a potential game because there does exist a single cost function, lowercase f, which depends upon two variables, so x and y. And the canonical standard assumptions are that f is strongly convex in one variable and strongly concave in the other variable. And then, as we've been saying, there is the word uniform to be kept in mind and remember. So it's strongly convex in x uniformly with respect to y and vice versa. So this uniform assumption is really simplifying. And at some point in time before the end of the day, I should come back and tell you, Francesco, you never told us about the gradients of functions that are only convex and not strongly convex. So you're or non-convex. So before you even wonder, the non-convex case, I am leaving it to you because I have no idea how to do it. But the convex case, I can say something about. All right, so now what happens is that you have a saddle problem, saddle dynamics, or primal descent, dual ascent, because oftentimes these x and y variables have the interpretation of arising from a constrained optimization problem where you want to minimize with respect to the x variable and maximize with respect to the dual variable. But okay, or you just call it saddle dynamics. So you have a function. So I should add a picture here. I apologize. I forgot to do that. You have a function which is, if it's convex, it looks like a cup going like this, right? If it's concave, the cup is going downward. A saddle point has the property, you must have seen this, it's like a saddle, literally. It goes up in one direction and down in the other, right? Okay. So now what you do is you just say that the first agent wishes to minimize f and therefore uses the gradient of descent, and the second agent wishes to maximize the function, and so therefore the second agent uses gradient ascent, going up, plus the gradient with respect to y. All right, and now under these assumptions, I guess I should have stated also that f needs to be differentiable. Forgive me, I forgot that assumption. It's very natural. Then the saddle dynamics f of s is infinitesimally strongly contracting with respect to the standard 2 norm, and the rate of contraction is the smallest of the two strong convexity parameters. Okay. Therefore, yes, there exists a unique globally exponentially stable point for the saddle dynamics, and that point is the saddle point of the function f. And the proof is very simple. How does the proof work? The proof works like this. The proof is, let's do it for the case of second differentiability, but that's not necessary, but it does become easier. So let's read this together. So it's another exercise in remembering the property of law. Okay, my computer, I had a glitch, but hopefully we are back now. Twice differentiable. So to prove contractivity, I need to study the log norm of the Jacobian. And I am using the 2 log norm. The 2 log norm, remember, right now I'm just going to say it instead of going back to the slide. It's lambda max, the largest eigenvalue of the symmetric part of the argument. So I need to take mu2, and I compute the Jacobian of this quantity here, right? So if you take the Jacobian of the gradient, you get the Hessian. So here you take the Jacobian with respect to x of the gradient with respect to x, you get the Hessian on the 1, 1 block. And then, of course, you get the Hessian also in the second block, but with respect to y. And one of them has a minus sign, the other one is a plus sign because of the definition. And then you take the Jacobian with respect to y of the gradient with respect to x. So this is a collection of mixed second order derivatives. All right, perfect. And then the same is x with respect to y. However, you all well know that second order mixed derivatives are symmetric. So if you differentiate first with respect to x and then with respect to y, or with respect to y, you get the same quantity, right? So the key thing to observe here is that magically, it just so happens to be the case that you have a minus sign here and a plus sign followed by exactly the same quantity. So your off-diagonal terms here are skew symmetric. One of the exercises that I will assign to you is a generalized version of this idea that if you are playing with the two norms, it really helps if the off-diagonal terms are skew symmetric. Nice things happen. What is it that happens? Oh, it's very simple. Because remember that mu2 of A is really the lambda max of A plus A transpose over 2. That means, by the way, without even writing lambda max, is that if you're calculating mu2 of A, it is the same as calculating mu2 of the symmetric part of it. Because once you've made it symmetric, if you try to make it symmetric again, it remains the same, right? So here, without even writing lambda max, which I guess I could have done anyway, my point is that whenever you see these two skew symmetric parts and we are working with the two norm, just substitute 0 because they go away. And now, yes, and now you're looking at lambda max of minus the Hessian and the Hessian. And now this one is strongly convex, therefore minus the Hessian gives you the largest eigenvalue is mu sub x, the strong convexity parameter of f with respect to the first argument. And then the other one is mu sub y. Does that make sense? So it's a simple proof. I'm not, this is a very simple case, strongly convex, strongly concave. So this is really the very first problem that you would do, but it's just to check and also do the calculations so that we warm up. Any questions? All right, next, let us look at problems that are not potential. So truly, generally, my cost function is very different from your cost function. They are not the same. And my cost, I will denote with the symbol J sub I. And I will use this notation from game theory, right? Xi is the decision of agent I, X minus I are the decisions of all of the other agents. So it's not so the functions Ji, J1, and J2 are not related to each other in general. So therefore, this is not a potential game, right? Okay, fine. And you aim to minimize your cost. Well, therefore, if you aim to minimize your cost, wouldn't it be natural if you're to just use gradient descent? So you're agent I, and you just say, oh, I'm just going to differentiate my own cost function with respect to my decision action, and I want to minimize that. Does that make sense? But of course, your cost of electricity depends upon the other people as well, right? So, and the other people's decisions are in X minus I. And so, what you do depends upon the others as well in a society. So if everybody applies this particular gradient, well, okay, this is some kind of a gradient system, right? But everybody has different cost functions. So what you can do, and here I wrote it horizontally, but maybe I should have written it vertically. So then I can write nabla 1 of J1, nabla 2 of J2, nabla, how many agents? Oh yeah, we got n agents of lowercase n. Okay, so how do I call that object, that vector with all of the partial derivatives, the gradients? I'm going to call it, people in some literature I've seen this word pseudo gradient, because it's not the gradient of a function. It's the gradient, you have n functions, and by the way, the functions depend upon xi and x minus I. So it's a bit of a weird object. So let's just call it pseudo gradient. And by the way, in game theory, they have this beautiful name. So they don't just call it the pseudo gradient dynamics. They would call it gradient plane. They use the word play. It's because they're players, right? So anyway, so I am playing the pseudo-gradient game. And my question is, as we were discussing, so I will erase this for my question is, does there exist a Nash equilibrium, and does the pseudo-gradient play converge to it exponentially fast, and is it robust to disturbances and blah blah blah? Does that make sense? Okay. Now look at the problem. It's extremely close to the standard version of the network contraction theorem, because you have n individual subsystems. And what are you going to assume about this xi dot equal to minus ji of xi comma x minus I? Well, how about we assume that OS lip of no, sorry. Well, I could OX lip of the gradient, or I can just assume. Why don't I assume convexity? So strong convexity of ji with respect to xi. So you want to minimize your cost, and you want your cost to be strongly convex, right? But your cost will depend upon the others as well, right? Or what is the canonical assumption when it depends upon the others? Well, the canonical assumption, I'll write it on top so that it is easier to read in the back. The other assumption is going to be Lipschitzness of nabla I ji with respect to x minus I, right? So your cost depends in a Lipschitz way upon the decision of others. Is this enough? Well, no, it's not enough, because the network contraction theorem, you need a third assumption. Now you take all of this, well, this coefficient, this is going to define coefficients Lij, and this is going to define coefficients mu I, right? The strong convexity parameters and the Lipschitz constants. And then what do you need to do? You need to put them together in the matrix, right? So here's the slides that I have written. Hopefully I did it right. Here, the first assumption is, maybe I should use numbers here instead of bullet points, but in any case, the first assumption is that strong convexity with respect to xi of ji. So ji is mu strongly convex uniformly. The second assumption is Lipschitzness of the gradient. By the way, I haven't studied this, but I am understanding that the Lipschitz constant of a function is not the same as the Lipschitz constant of the gradient, right? So there, you just here, this is not the Lipschitz constant of j. This is the Lipschitz constant of the gradient of j. Fine. And then you construct a matrix, which I'm not gonna do because you already know how you do it. You put the contraction rate on the diagonal, and it's also very natural. You need to assume it that that's Hurwitz. If that Metzler matrix is Hurwitz, then the pseudo-gradient play is infinitesimally strongly contracting with respect to an appropriate norm, which is you construct the gain matrix, you compute the optimal norm for the gain matrix, that's your aggregating norm. From that, you get to the composite norm, and that's the correct norm. And the rate at which you are contracting is the spectral scissa of the gain matrix, the absolute value of it, because the spectral scissa is going to be negative. Does it make sense? Now, 1, 2, and 3 here are sufficient conditions for strong contractivity. Maybe you're strongly contracting even if you don't satisfy 1, 2, and 3. Either way, if you are strongly, if pseudo-gradient play is strongly contracted, well then, in any case, there exists a unique globally exponentially stable Nash equilibrium, right? And then, as you write down the condition, you verify that it satisfies the Nash conditions. And by the way, when I write here, this theorem is two parts. The second part is obvious. The second part is the continuous time bound contraction theorem. It tells you that if you have a dynamics and it's contracting, it has a unique point. And in this particular setup with the pseudo gradient, that point is a Nash equilibrium. And you could be contracting with respect to any norm. It does not need to be a composite norm. It could be a norm that you work with. So I broke down this theorem in two parts because I wanted to clarify that these are sufficient conditions for contractivity, but contractivity could happen anyway, and then you get to the Nash equilibrium. All right, there's another game that people play. It's called best response. So basically, you could say, Francesco, if I know my cost function, I could just compute the optimal solution, right? Why don't I just go directly to the optimal solution? Why am I following the gradient when I already know what is the best response? So in other words, if you are trying to minimize, if you're trying to minimize your cost function ji, imagine that you could compute the argmin of capital Ji with respect to lowercase I. What does that mean? That means that as a function of the other agents' decisions, you know what's your optimal decision. So, by the way, you cannot optimize the function ji without knowing the other agents. So your optimal strategy is not a point. It's a function. It's a strategy. It depends upon what the adversaries are doing. Well, sorry, not that I mean for you to be my adversaries, but right. So it's not. I want to make the case is that this is not a point. It's a function. It depends upon the other people's. So the best response is a function of x minus I for agent I. So let's call it BR, best response. So then you could say, you know what? Why don't I go directly to the best response? So the continuous time dynamical system would say xi is equal to best response function of x minus I minus xi. Because now, right, this is the continuous time equation that you would write. So if you want to go, if you write x dot uguale a minus x, then you go to a, right? You go to the value a exponentially quickly. Okay, so this is in continuous time. You could also say, I don't know why I need to do it. I do a flow, Francesco. Let's just do it in discrete time. What if I jump there directly? K plus 1 is equal to, no, sorry, xi at time k plus 1 is equal to best response for agent I as a function of x minus I at time k. How about that? Let me write this better, more elegantly. xi at time k plus 1 is equal to best response for agent I, function of the decisions of the other agents at the previous time, at time k, right? So this is continuous time best response, and this is discrete time best response, right? So now I have defined three dynamics for you: continuous time pseudogradients. I don't know how to make sense of discrete time pseudogradients, so I'm not going to define it. Continuous time best response and discrete time best response. And then now I kind of wonder, can I write contractivity test for, well, we've done it for pseudogradient in continuous time. Can I write continuous time pseudogradient? No, sorry. Can I analyze the contractivity of best response in continuous and discrete time? And so the answer, yes, you can. And everything that you can imagine is going to be true. And what can you imagine? You should imagine that more or less the same thing are going to happen. And so you are going to assume that ji is mu I strongly convex. Did you symbol? Did I use mu I in the previous slide? I think I may, by mistake, I've used a different symbol here. But anyway, strong convexity, Lipschitzness of ji. I can show that this implies that the best response is, so making the same assumption on ji, that the best response I is Lipschitz with respect to j. So here, the little result is that I don't need to take derivative of this. The old condition implies also well behavior here, but the Lipschitz constant is different. The Lipschitz constant is Lij over mu I. Does that make sense? What I'm trying to do here? I don't want to make a different assumption from before. Then why would it be true that the global minimum of a strongly convex function parameterized is of the form L over mu? Why would that be true? Well, I thought we saw that yesterday. Yesterday we saw that. Again, it's the same result. We saw that this fixed point is the Lipschitz function with the Lipschitz constant L over C, right? And the problem here is, what is the Lipschitz constant of the best response, which is the optimal solution with respect to xi as a function of x minus I. And so the Lipschitz constant is going to be L over mu, because L is the Lipschitz constant with which x minus I affects the behavior of xi, and that's the contraction rate. So this particular line here, which I am writing, is again an application of what we saw yesterday when we did the parameterized fixed point problem. So now I can construct a gain matrix for this continuous time play, the best response play, and it is not going to be the same gain matrix as before, right? It is going to be a different matrix, because this, well, the off-diagonal terms are going to have Lij over mu I, and even the diagonal terms are going to be different, because the diagonal terms are going to be the contractivity rate of this piece here What is the contractivity rate of this? You can read it off of the formula. What is the contractivity rate of this dynamics? Because, let me just present it for you in a different format. Xi dot equal to A minus Xi. Now, A does not depend upon Xi. That's the point. This term does not depend upon. So when you take the Jacobian, this goes away. And now it's just, the Jacobian of this is just minus identity. So therefore, the contraction rate is -1. All right. So this particular gain matrix is going to have -1, -1, -1, -1, and then it will have Lij divided by mu I on all of the terms of the uptime. So it's a different gain matrix from before. But the result is that the dynamics, by the way, the dynamics is called best response, but the dynamics is not best response vector, the best response map. It's best response minus identity map, right? So here you read it off. And so the vector field is not best response, it's best response minus identity is infinitesimally contracting with respect to the same norm as before. Something came to mind that I want to do immediately. Cannot make it happen now. All right, I'll work at that. I'll work at that later. All right. So here's the point. The point is that if you are doing pseudo gradients in continuous time, you can define a certain gain matrix, which is like that, and it's Metzler. If you're working with best response, you can define its gain matrix, which looks like that. If you are working with discrete time best response, you can define a matrix which has all just Lipschitz constants. And so what would that look like? So we wrote xi at time k plus 1 is equal to best response for agent I as a function of xi at time k. If you take the Jacobian with respect to, no, my mistake, minus I. So your decision at time k plus 1 depends upon the decisions of others at time k. So what is the Jacobian of this quantity with respect to itself? So if I take the partial with respect to xi of the right-hand side, how much do I get? 0, because the right-hand side does not depend upon xi. So I have a 0 here, right? So the Jacobian matrix for the discrete time best response has 0 on the main diagonal. And then it has the same off-diagonal terms as the continuous time best response, because the continuous time best response would have been best response I, x minus I at time t, okay, fine, minus xi at time t. When I take the mixed derivatives, so when I take the partial derivative with respect to x minus I, you get Li. So that's why you get this here. So what have I done here? I have written down the gain matrix in continuous time for pseudo gradient, in continuous time for best response, and in discrete time for best response. And now, if you go study Metzler matrices and positive matrices, which are briefly described in the book, or I can give you better references, it turns out that these are equivalent statements. So this matrix being Hurwitz is if and only if that matrix is being Hurwitz, if and only if this matrix being not Hurwitz, because that's discrete time. It's Schur stable, not Hurwitz stable, right? So the eigenvalues are inside the strict unit circle. Does that make sense? So this is good news. It's exact. So all of these three things converge and are contracting with the same rate, if and only if. All right, perfect. Last comment. If you look at aggregative gains, which are of this special form, the cost functions that the individual agents have a particular expression. They depend upon not the individual behaviors of every other agent, but rather upon the cumulative behavior of all the other agents. For example, people typically just do the sum of all of the energy requests. Whether you do the sum or you do the average, it's the same, right? Because you're just summing the other requests, right? So here, basically, JI is lowercase fi. Doesn't matter the choice of symbols, but it doesn't depend upon x minus I in arbitrary way. It depends upon it only through the aggregate demand or the average demand. It doesn't matter, right? So now when you compute all of the Jacobians that you have to compute, there will be some simplifications because everything will simplify. And now, because J is equal to Fi, right? Now, Fi here is a function of two arguments, not of n arguments, right? One argument is your own state, and the other argument is the aggregate state, the average state of everybody else. So when you take the partial derivatives of Ji, well, it's going to have to be the partial derivative either with respect to the first or the second argument. And the function lowercase fi has therefore only two partial derivatives that are important, one with respect to its own state and the other one with respect to the aggregate, right? So let's assume that the aggregate cost function lowercase fi is strongly convex with respect to the first argument and Lipschitz with respect to the second argument. Lipschitz with respect to the second argument. Well, then it turns out that all of these tests of Hurwitzness and Schur stability for the big matrices, they all simplify down to being just that mu I is larger than Li. So if each agent has an aggregate cost function lowercase fi, well, if Ji is of that form, then you don't have n coefficients or n square coefficients to put in a matrix. You just have two coefficients for each agent, mu I and Li. And you just need mu I to be larger than Ni. And if that's so, then I can prove that those gain matrices are all stable, either Hurwitz or Schur. Does that make sense? So very, very simple. The game is contracting, strongly contracting, everything works. Professor Zampieri has a fantastic question. This is a sufficient condition for Hurwitzness of that matrix. It is only sufficient. It is only sufficient. All right. End of discussion of games. Does that make sense? All right, this was the applications of the network contraction theorem and contractivity. We did the games. All right. Are you tired? Would you like a break or should we proceed to the next topic? How about you give me 5 minutes and I show you what I had skipped earlier. I want to show you briefly what are the other properties. I'm not going to prove them. I'm just going to state them and then we take a break. And the properties are these additional properties that I didn't cover yet. Property number one is entrainment. So entrainment is very important. We live on a 24-hour cycle and our own biological clocks are entrained to sunlight. And so entrainment is the fact that if you have a vector field F, which is a function of time, and it could be of the form f1 of x plus u of t, where u is periodic. It could be that the periodicity comes from an additive input. It doesn't matter. It does not matter. I have a time periodic vector field, and the dependence upon time is periodic. And then I assume, so basically, it's periodic with respect to time, and the other assumption is that the vector field is contracting. If so, then you entrain. What does that mean? It means that there exists a unique periodic solution of the differential equation x star, that's the unique periodic solution, and every trajectory, no matter where you start, will entrain, which is to say, will converge exponentially fast to the periodic solution. Does that make sense? Entrainment. Again, the power here is both the existence of the periodic solution and the global exponential convergence to the periodic solution. This is not easy to achieve without contraction theory. Second property, I have a dynamical system f of x. I know it's contracting, but there is a perturbation. There is a perturbation. Now, it's not an additive perturbation coming from an exogenous signal. That is part of the incremental ISS theorem. This is an unmodeled dynamics, which changes the dynamics, delta. So actually, this particular result is even more similar to what I was trying to say at the beginning of the hour. What assumptions are you going to make? Well, I'm going to make the natural assumption that the nominal system is contracting, right? And then we remember that the one-sided ellipsis constant satisfies the real part of a complex number property. So in other words, OSL of f plus delta is upper bounded by OSL of f plus OSL of delta. And then if you remember, mu of a matrix is always upper bounded by the induced norm of the matrix. This means that this is upper bounded by OSL f plus induced norm of delta, plus Lipschitz constant of delta. So, standard assumption, this is contracting. The other one, well, if it's contracting, great. But if I don't know anything about it, maybe natural to just say, let's imagine that delta is either expansive with rate d, or the Lipschitz constant of delta is equal to d. And now, what do you need in order to have contractivity? Well, you need that the rate of contraction c is larger than d. So you measure the contractivity of the nominal system, you measure the one-sided Lipschitz constant or the Lipschitz constant of the disturbance, and you ask that c is greater than d. And if so, the resulting perturbed system is contracting, the rate of contraction diminishes. It is c minus d, it's the gap, right? And the you also know a little bit about what happens to the fixed point. So because the original system is contracting, the perturbed system is contracting. If they're both time invariant, you know that an equilibrium point must exist. So then you can ask yourself the question, how much does the fixed point move by? And it moves by a measure of how much is the effect of the disturbance at the old equilibrium divided by the contraction rate c minus d. Now, I have more slides about the effect of delays. So people may be interested in your dynamics at time t depends upon your current state and the value of your state in the past. And it's of interest to do this for a single system, and it's of interest to do this for interconnection of systems where your evolution is a function of your state, the state of others at this time, and the state of others at previous times. I'm not going to go into the details, but you can write theorems that will give you convergence to the equilibrium, or actually, a generalized version of ISS for this type of systems. As promised, that was relatively fast. Let's take a break, and I will see you back shortly. Thank you. Very well. Welcome back after the break. Allow me to remind you where we are. You really cannot see the gray items on my screen, unfortunately, here in the room, but the point is that we have studied the history and resources. We have studied the basic definitions in discrete and continuous time for vector spaces. We've seen various examples, and we've seen various gradient flows. We've seen some neural networks. We've seen the Luret model. And then we've studied all the properties of contracting dynamics. We've, for example, studied the Euler discretization, right? We studied the incremental ISS. We studied and briefly mentioned entrainment, the network contraction theorems, all sorts of properties. The examples here were gradients, neural networks, the Luret model, right? And then we've looked at Nash as Nash equilibria as an example application of the network contraction theorem. So now I would like to show you an example application that will come with even new example systems for using the incremental ISS property. So you may say, Francesco, why do I care about the incremental ISS? The reality is we have already used it because we've used the incremental ISS to establish the solutions of parameterized fixed point problems. We've seen that the solution of parameterized fixed point problem is a Lipschitz function with constant L over C, where L and C are the Lipschitz constant and the contraction rate with which the disturbance in the state appears in the fixed point problem. So now we know the incremental ISS theorem is fundamental. So let me now show you an example problem, how you can use it, how you want to use it. So let me go to this problem called equilibrium tracking. And to do equilibrium tracking, I'm actually going to define a new property, an additional property of contracting systems. And let me give you a little bit of motivation for the application. And also let me justify a little bit that so far I have looked at many optimization problems and I have given to you solutions in continuous time. And you may tell me, Francesco, why did you do it in continuous time? Because my computer is digital and it performs discrete time calculations. So you should give me an algorithm, a discrete time dynamical system, not a continuous time dynamical system. I have two answers to that perfectly well-posed question, or maybe even three. One is because I haven't had the time to study the discrete time problem. All right, let me just say that. Two, I did show you the Euler theorem, the Euler contractivity theorem. So when I show you a continuous time dynamical system that is strongly contracting, then you should know that if you go to that theorem, that's telling you that if you do the Euler discretization of that continuous time dynamics with an appropriate step size, it will converge. It will be a contraction. So if I do continuous time, the discrete time is not too far away. Question?
Fixed points the same?
Oh yeah. Oh yes, of course. Good question. Maybe my slides did not say that. So that's my shortcoming. Absolutely the same. Oh yeah. It's trivial. That's one line, not even one line. If you just change it. By the way, I will let you read. When you construct the discretization of a continuous time dynamical system, and you do the Euler step, identity plus alpha F, something like that. Because you may think, oh, Francesco, your contraction rate C, but if I multiply the vector field F by the number 2, then the contraction rate will be doubling as well. So then you think, oh, I now have a faster dynamical system. And in continuous time, that's true. If you just multiply the vector field by 2, it will double the contraction rate. And that's because the one-sided Lipschitz constant has the homogeneity property. So if you multiply by 2, the 2 comes out. But if you go and check, when you discretize it and you have to choose the step size, it turns out that this trick of multiplying by 2 does not work, because it will turn out that you need to use a smaller step size. And so, in fact, I don't know if you remember in that slide, I defined something called the condition number, which was the ratio between the contraction rate and the Lipschitz constant. Right, actually the other way around, the Lipschitz constant. So when you multiply by 2 your vector field, yes, your contraction rate doubles. However, unfortunately, also the Lipschitz constant doubles. And so the condition number of your system has unchanged. So if you think I'm going to be faster by just scaling it up, it doesn't work. It apparently works in continuous time, but it doesn't really work when you discretize it. All right, anyway, so this was a detour, an open parenthesis on why is it a good idea to do continuous time anyway. And that's because, well, as I said, I haven't had a chance to study it. There's a limited amount of time. Literally, there's a forward Euler theorem, so you can do it. Fine. On this slide, I have a third reason why are we doing continuous time. There has been historically a lot of interest in solving optimization problems using continuous time dynamical systems. Why? Well, as I mentioned, the first papers, first of all, it's actually simpler to treat. So the very first paper by Haro, Urchwich, and I forgot to mention the name of Uzawa, those scientists who defined the primal dual gradient descent, was in continuous time. So in fact, that even predates. And then since that, there's just been a lot of interest, like neural networks are presumed to solve optimization problems. People have been studying just analog circuits. You build an analog circuit that solves the problem. And analog circuits have the potential to be incredibly fast. So for example, you may build circuits that have incredibly high bandwidth, and maybe you can do the computation super fast with an analog circuits. And there are also problems that anyway, so even Professor Zampieri, who's here with us today, wrote about, you know, writing continuous time optimizers that play the role of controllers, and so on and so forth. In the second half of this slide right now, I will tell you about something called feedback optimization, which is also continuous time. All right, what is the problem that I am interested in? Well, at a high level, I want to look at a problem like this, very simple. I want to look at a dynamical system that solves an optimization problem. So the example that I started with yesterday or the day before yesterday was just a strongly convex function, lowercase f, and the contracting dynamics is the gradient descent, right? Minus not one. But then by now, since then, I've shown you plenty of examples, right? So let me just, so there's a whole host of examples. And here I've actually more or less shown to you all of these examples. To be honest, I cut out from the slide deck the linear inequality constraint. So in this slide, the only new thing is that when I have a linear inequality, there is a contracting dynamics with primal dual that will solve that is strongly contracting with the given rate that I can compute. It's messy, but numerically I can always do that. That will solve the linear inequality constraint strong convex optimization problem. Okay, it's actually very interesting because there are a lot of problems in which you have a resource that you want to allocate, and the resource has to satisfy linear inequality, and so it's just it's very useful. But I haven't had a chance to show it to you so far. And there's an N here. This is to do with recent work by Mihailo Jovanovic. He uses the Moreau envelope. It's another story in optimization, like the proximal gradient and so on and so forth. But it can all be done. The point is that I have many convex optimization problems, and I have many dynamical systems that are contracting and that solve the problem. In some cases, the constraints, but by the way, you can solve constraint problems using primal dual approaches, or in some cases, you can solve constraint problems using projected gradients, right? So depending upon which of these algorithms is faster, can you compute in closed form the projection, and so on and so forth. So the choice of which dynamical system to use, I'm not going to talk about, but it's widely studied subject. The point that I'm interested in is that I'm interested in not just a static optimization problem. We are interested in time-varying optimization problems. So problems that depend upon a parameter, and the parameter theta may very well will be in general a function of time. And by the way, it could even just be time. Time, it's fine. It's just theta of t is equal to t. For theta of t is equal to t, and it could be a vector. Theta is not a scalar, it's a vector. So do t, and then sine of t, I don't know, and then something that genuinely just depends upon time. So I'm just going to call this parameter theta. And now, as I have mentioned to you yesterday, whether I call that theta, or I call it a disturbance d, or I call it an input u, it doesn't matter. It's just an exogenous signal, and I'm just going to assume, what am I going to assume? I'm going to assume strong contractivity with respect to x and Lipschitz with respect to theta today instead of u, but it's the same, right? All right, perfect. So these are the standard assumptions. So if I use theta, the only novelty here, really fundamental, is that maybe capital theta is this particular symbol. Yesterday I was using script u or something like that for the set where the input takes value, but it is the same. And because it is the same, of course, I satisfy the incremental ISS property, right? So the error, what do I mean by error here? Well, actually, let's slow down here. So the incremental ISS talks about any two solutions of the dynamical system. X dot equal to f of x of t, comma, theta of t. So what the incremental ISS theorem tells you that the distance between any two trajectories of the system, this is the distance, this is the distance. Well, actually, to be even more precise, this is the distance without the c. The distance satisfies my super friendly first order exponentially stable differential inequality. So the derivative of the distance is upper bounded by minus c, the distance, plus the Lipschitz constant L times the forcing term, and the forcing term is the different parameters that you use for the solution X and the solution Y. Okay. However, I have okay, let's think about what it is that we want to achieve. I have a dynamical system that, and by the way, I did not say it, but let me go back. Let me go back even here. Here, when I say that the dynamics solves the optimization problem, what I mean to say is that the equilibrium point for the dynamics is the global minimum of the cost function, right? So the dynamics is not arbitrary. It's solving the convex optimization problem, right? All right, fine. Right. So what is it that I want to achieve? Well, because of the Lipschitz assumption, contractivity and Lipschitz, I know that for each value of theta that you give me, there exists a unique fixed point. So we've discussed this ad nauseam. By now you should be tired of it, right? So there is a function x star from the set of parameters into, okay, I could even write x, or in any case, Rn, the state of the system. So you give me a value of the parameter, there is a global optimum, and my dynamics will go to it. And then you play the game that, oh, I'm going to change the parameter. And then I am the contracting dynamics. Okay, I'm trying to go there. And then you change the parameter, and I'm trying to go there, right? So because the unique, first of all, we already understand x star is not a point. X star, the fixed point, is a map. And if I tell you that theta depends upon time, well, then time gets mapped into theta of time, that gets mapped into x star of theta of time. So this is now a trajectory, right? So now you have a map from time to a curve. And that curve, what is that curve? That's the curve of the time-dependent optimal solution to your convex optimization problem. That's the optimum as a function of time. And that's an interesting trajectory. That's where you would like to be, right? You would like to be at the optimum. But you're not at the optimum. What is your trajectory? You are following, you're trying to go there. You are x of t, and you are trying to follow as best as you can x star of theta of t. Now, what do you care about as a control designer? You care about the distance between these two quantities. So that is the quantity that you are interested in. The error, your error, I'm going to go back previous slide. Your error is not the distance between any two trajectories of your system. Your error that you're interested in is the distance between your trajectory and the trajectory of the optimal solutions, which is x star of theta of t. Does that make sense? So it's still two curves, though. You have two curves, and the two curves, maybe you're interested in distance between two curves. But when you're talking about the distance between two curves and how do they change in time, it should not be too far away, right? It's still, maybe I can still use contraction theory because I have two curves. I'm just comparing them, right? So how do I do that? So, and we already said, because of the parameterized fixed point problem or the parameterized Banach contraction theorem in continuous time, the equilibrium map is Lipschitz with constant L over C. But then again, really, I'm not interested in that map. I'm interested in the map from T all the way to x star of theta of T. So what's the Lipschitz constant of this map, which is not the same as that? So that's another question that will have to be answered at some point in time. Okay, here's the theorem, which I will show you in a second. And the theorem is that, I would like you all to see it. All right, the theorem is that the error is the norm of x of t minus x star of theta of t. I know the notation is a little heavy, that's why I'm going slowly. But really, it's the correct error. That's what you really care about, is where are you and where is the optimal point? That's your set point. You would like to go there, right? But that point is moving. So you're tracking the equilibrium or tracking the global optimum of the cost function. your error satisfies a friendly first order, exponentially stable differential inequality. Good news. Let's look at it in detail. So literally, you may just want to write error, so that way it's easier to read. So this is the error, is upper bounded with minus c times the error plus a forcing term. So two things. One is that the error is the new error is decreasing with rate c, just like the old distance. So that's kind of surprising. So we should understand that. And then the second thing is what happens to the forcing term, and the forcing term is L over C times, what is that? That's the speed of the parameter. Well, the parameter theta depends upon time. The parameter theta is a vector of parameters. There is a velocity vector theta dot, but the velocity vector is in the space of parameter changes. I am interested, well, I need to have a norm, right? I know I need to have a norm in the space theta, because otherwise I cannot even talk about Lipschitzness of f with respect to theta, right? So this is the speed of the parameter because it's the norm of theta dot. And it makes sense because if the parameter is moving very, very, very slowly, it's essentially stationary, well, then that error that it's being injected is going to be very slow. And you can already predict that if you look at this ODE, the error will become very small, right? But if the parameter moves very rapidly and my equilibrium is changing very rapidly, yeah, then I will have a larger tracking error, right? So it makes sense that the tracking error would be dependent upon the speed of the parameter, right? Okay, so we need to understand why do we get this ODE. And let me show you the proof because it's really immediate. It goes like this. So maybe the setup is way longer than the proof. The setup is like this. Okay, I have my time parameter dependent ODE, but the parameter is function of time. I know that I have contractivity and Lipschitzness. So I have two trajectories that I care about. One is the trajectory x of t, and then I have this other function of time, which is not the solution of an ordinary differential equation. It's where is the optimal point, you know? And this optimal point is implicitly defined by it's the fixed point of the equation, right? It solves the equation, right? This is a static map and it solves it. That's the way it's defined, right? Perfect. Now, wouldn't it be true that it's the usual trick. The usual trick is that you sum and subtract the same quantity. If this equation holds, then let me show you another equation that holds. The derivative with respect to time of x star of theta of time is equal to itself. The derivative with respect to time of x star of theta of time. And then I sum f on the right-hand side. So then I get that the derivative with respect to time of x star of theta of t is equal to f of x star of theta of t. And then I need to sum that. Let me call that v. So let us consider the ODE. Okay, let me go here. Let me define a new system, a new dynamical system called, let me call it auxiliary, to explain that it is not the old one. It looks like the old one. It's x star equal to f of x comma theta. But then I introduce a signal, a controller, which is additive. Let's call it v for a second. And now it's obvious that my equilibrium trajectory x star of theta is a solution to the auxiliary system, where as input to the auxiliary system, I put the derivative with respect to time of theta of t. And why is that true? Because theta of t, because x of theta of t satisfies the equilibrium equation. And then I'm just basically summing zero to the equation, right? Any questions? So the statement that I am making is this. If you define the auxiliary system like that, then the equilibrium trajectory is the solution when you use v of t equal to x dot of theta of t. So maybe it's mind-bending, but it's really elementary. You don't. And the solution that you are actually following, your trajectory, is not a solution to the, it also is a solution to the auxiliary system when you use V equal to 0, because in the real system, you don't have the benefit of knowing where is x dot of theta of t going. If you knew that, then you could maybe use that to track even better. But right now, let me assume that I do not know anything about theta of t. Now, what have I achieved? I have set myself up in such a way that the error that I care about, the distance between these two trajectories, the error that I care about is the distance between two curves. And now I found a dynamical system for which both curves are a solution. And now I just hope that the dynamical system is contracting and has a certain Lipschitz constant. So let's just calculate the contractivity rate and the Lipschitz constant of the auxiliary system. Does that make sense? Because then I can use the incremental ISS property on the auxiliary system, and I will get the bounds that I want, the bounds of the error that I wanted. Any questions? And the proof ends right here because, sorry, if it's a little bit abrupt, because the contractivity rate of the auxiliary system, if you take the partial with respect to x, V plays no role. And so the contractivity rate of the auxiliary system is the same as the contractivity rate of the original system. And then you have to put in the Lipschitz constant of, so this is minus C. And then you need to put in the Lipschitz constant. How does the parameter V enter in the auxiliary system? And that number, the Lipschitz constant of the right-hand side with respect to V, well, it's just 1, because V does not appear in F, right? It's the new signal I just introduced. So then I know that this is 1, right? Perfect, I'm almost done. Therefore, I can just apply the incremental ISS property. And the incremental ISS property, what will it say? It will say this, the first row. I hope you can all see it. It will say that the distance between the two trajectories that I care about, which is really the tracking error, satisfies time derivative. So E dot upper bounded by minus CE. Perfect. Now I've explained the first part of the theorem that I really cared about. Why is it true that my error decreases exponentially fast? Minus E plus Lipschitz constant. How much is it? 1 times the norm, the distance between the two V. And we said V equal to 0 is the one that generates one trajectory. V equal to x dot of x star of theta of t, the derivative, sorry, is this is the other signal. So then inside this norm, I need to put 0 minus x dot star of theta of t. It's just more complicated to read it than to actually. Okay. Finally, this is an exercise in the list of exercises that I am going to give you. There is a trivial result that I would like you to prove. If I have y equal to t of x, t is Lipschitz, and we are on a vector space with norms. Suppose that I consider a problem where I have y of t equal to t of x of t. Suppose that L is equal to the Lipschitz constant of t. And now I want to write a bound like this. I want to write y dot of t, but upper bounded by something that multiplies x dot of t. Is this equation star true at all with respect to some constant? Don't worry, it'll be in the PDF that I send you. So hold on a second, but the Lipschitz constant t here, what does that mean? That means that t of y1, no, sorry, my mistake. So the fact that it's, this is super ugly, Francesco. You can do this better. Yeah, y1 minus y2, which is equal to t of x1 minus t of x2. But because it's Lipschitz, it's L x1 minus x2. So here I didn't write anything. I just wrote the Lipschitz definition. So we know that if you have a finite variation in x, this gives you a finite variation in y modulated, right, amplified or attenuated by the constant L. This is the definition of Lipschitz constant. So therefore, please believe me when I tell you that here you put an L. Huh? Now, this is a finite variation, and the equation star is an infinitesimal condition. And I would like one of the exercises that I will give you, for those of you interested, will be to prove that this is true under mild condition, and the proof is 2 lines. Let's say 3. So now, why is this useful? Because I need to, my last step in this proof is precisely to prove that the norm of x star dot of theta of t is upper bounded by the norm of theta dot modulated by the Lipschitz constant. And we know that the Lipschitz constant, bless you, the Lipschitz constant of x star is L over C. We know that because, okay, it's the 3rd time I say it today, it's the parameterized fixed point problem that we discussed yesterday. So here, the first row here is 1 times 0 minus, don't worry about the 1, the 0, and the minus, because they are nothing, right? So I have the norm of the velocity in the x space as a function of so I have the speed in the x space as a function of the speed in the parameter space, and they are related through the Lipschitz constant. And the Lipschitz constant in this case is L over C. Does that make sense? End of proof. It took me longer, but it was just to teach you again. So now, let's go back to the statement. I want to make one important point. And the point is that, before I go to the next slide, is that C, the contractivity rate, appears twice in the right-hand side. That is not the old ISS theorem. In the ISS theorem, the constant C appears only once, but here it appears twice. Why does it appear twice? Because of the fixed point property, C appears at the denominator of the forcing term. So in other words, if your system is highly contracting, which means that your optimization problem is strongly convex, when you change the parameter, the fixed point moves very little. Perfect. And then on top of that, when that point is moving very little, still the error is decreasing at rate C. So there are 2 C's that are coming to help you in this problem. C appears twice. So now the consequences of this tracking error ODE, but it's not an ODE, it's an ordinary differential inequality. The consequences is that after the transient due to the initial condition expires, and you ask yourself the question, how big is the error going to be in the future? This is going to be depending upon the speed of the parameter, right? But the coefficient, the coefficient is not going to be L over C. It's going to be L over C squared. Because you need to set the left-hand side to 0. You bring this to the left-hand side, and you divide by C, you get L over C squared. So essentially, affectionately, when I talk to my to friends, and I say, this is the L over C square result, because it's not L over C. Now you have a square that comes to, well, does it come to help you? Well, it depends. If the contraction rate is greater than 1, it helps you. If it is less than 1, well, not quite, because 1 over C is going to be greater than 1. So you're slowing down. Does that make sense? So, but the point is that your system is contracting, both the nominal system, the auxiliary system, so everything is good, which means that if the speed of the parameter is bounded, the error is bounded, I could write the Cronwall upper bound with the details of the transient, which I'm not worrying about here. I have this asymptotic bound. Remember yesterday I mentioned there's a finite gain result. So if the parameter changes has finite bounded energy, then the bounded energy of the then even the error has bounded energy. If the input vanishes, the output vanishes, because this differential inequality says that. If the speed at which the parameter changes vanishes exponentially fast with rate h, now you have a linear system which is exponentially stable with rate c, forced by a signal which is exponentially decaying with rate h. Do you remember from your controls class at what rate do you go to 0 in that case? it's a little exercise. It's the slowest of the two numbers. So it's easy. You can just write the solution and you can verify that it is an exponentially decaying rate with the minimum of the two rates, the smallest of the two rates, C and H. And we talked about entrainment. It just so happens to be the case that you put in a sinusoid as a disturbance, as you know, your parameter is changing sinusoidally, then it turns out that you are tracking the sinusoidal parameter in a periodic manner because of the entrainment property of contracting systems. Does that make sense? I have two pictures here. Here's just, I have two optimization problems. One is an equality constraint. The other one is the inequality constraints that I did not show you the dynamics for. I have plots of the exact of the equilibrium trajectory in Nash and the actual solution of the ODE in solid. So what do you see? You see that the red solid curve exhibits a little bit of oscillations, and then it tracks, right? That's the transient that is exponentially decaying with rate C. Right, so you see it here. This is the transient in the red curve, in the blue and the green curves. But then after that, you will see that the solid curves in red, the blue and green are tracking the dashed curves, which are the equilibrium trajectories. And this is the same for the inequality constraint. In the inequality constraint problem is really challenging and interesting. As you have a periodicity here, the optimal solution varies in a way that is not even differentiable, but still you can, the solution to my dynamics is smooth. The dynamics is smooth, that tracks it. And so anyway, so there are the transit at the beginning and then you're tracking. Now, I will tell you an area of current research is the following. I have a time varying parameter and I want the dynamics to be contracting with respect to the time invariant norm. So what I mean by that is that my dynamics is contracting independently of time. But what if the dependence upon time appears so pervasively in the problem definition, for example, here. So we've looked at the primal dual, right? And we've written down that the Arrow-Hurwitz dynamics is contracting. We proved it in great detail. So if you want to minimize this strongly convex function subject to an equality constraint, you have seen the proof that this ODE is strongly contracting with the rate. It was a bit of a mess, right? We did the proof with the LMI. Now, in the LMI proof, you should remember that the P matrix had something like identity or a pi, doesn't matter, but there was the A matrix there. There was an A matrix, if you remember, if you go back. Now, I need P to be time invariant, otherwise my current theory does not work. So in other words, when I think about where can theta appear, I can put theta inside F, I can put theta inside B, but if I put theta inside A, I have got a problem. Because now the norm with respect to which I am hoping to prove contractivity is time dependent. And I have not yet explained to you how do you do contractivity with respect to a time varying norm. Now, there exists such a theory. It's hinted at in the lecture notes, and it is an area we're trying to write this thing down carefully so that we can handle optimization problems where the natural dynamics that's contracting may be contracting with respect to time varying norm. And basically, essentially, it's a very simple game. You're going to take time derivative of matters and there will be extra terms, and you need to worry about the extra terms. Okay. All right. This is the end of the tracking error. Now it's 12. Allow me to show you a quick application of this to a control relevant problem, and then we go for lunch. So let us consider a problem like this, it's called feedback optimization. In feedback optimization, you are given a plant, it's a dynamical system, but we're going to make an assumption that you have already designed a controller, a feedback controller, and that's happening very quickly. At a fast time scale, your plant is stable. It's fast and stable, loosely speaking. So, and then still, maybe you're regulating the set point of your chemical plants, and then the chemical plant itself is quickly converging to the new set point or something, right? In any case, there is a signal. Here it's called U, but it could be, I could have a difference. If it's a reference signal, maybe I should be calling it R. It doesn't matter. I have a signal U that affects the plant. The plant is subject to a disturbance. The disturbance does not happen at the fast time scale. It happens at the slower time scale. And I get an output Y. Now, I would like to minimize U squared plus Y squared. So I want to use little control, and I want to make sure that Y is small. Like a linear quadratic regulator theory where you penalize the control action and you penalize the output. Actually, yeah, does that make sense? So I am going to define a problem, a cost function, where I say that I have a cost function of U, a cost function of Y, and Y is the output of the plant, which is determined by the input, the two inputs, the input U and the disturbance W. Really, I should write a more complicated problem where I put in the dynamics of the plant. But right now, I'm assuming the dynamics is very fast. And so I just use the input-output map as if it was static. Does that make sense? How do I solve this problem? Well, if I were super fast and I have a super powerful computer, I can immediately solve the problem and plug in the optimal solution U. Maybe I'm so fast, but in some cases, perhaps you want to be able to design a controller. Maybe you will design an optimizer, and while the optimizer is running, things are also running. So you write an ODE that says minimize as a function of U, design the controller for U, so compute U as a solution of an ordinary differential equation where you are optimizing the cost function subject to the constraints. Okay. All right, fine. So Emiliano has donated to me this slide where he shows that this idea of feedback optimization has found a lot of interesting applications, which I'm not really. So let's do a very specific example here. Suppose that I have a linear time invariant plant. So I don't know how to make it easier than this. AX plus PU, and then there is a disturbance W pre-multiplied by the matrix E. And I want A is Hurwitz, so it's stable, and I put a small parameter epsilon so that this plant runs quickly. So it's fast and stable, like I was saying. In the limit, as epsilon goes to 0, which is called the singular perturbation limit, because you're letting the time scale for the dynamics, be such that you're basically at equilibrium. What is the steady state map from U and W to Y? Well, that steady state map, it's easy. You probably have studied it. It's you can calculate it, right? This is the matrix minus C A inverse B, D minus C A inverse. Because I am lazy, I'm just going to call this Y sub U and Y sub W. So that's Y sub U is the map from U to W. From U to Y, and Y sub W is the map from W to Y. Right. So it's just linear, super easy. It's two matrices. Okay, fine. So now I want to minimize a problem where I want to minimize this cost, a phi of U, a cost in U plus a cost in W, subject to the steady state map, right? Notice that this optimization problem. What is this optimization problem? Well, first of all, for a split second, if I take I can eliminate Y, right? I just plug in Y sub U plus Y sub W. I plug it in there, right? So I'm trying to minimize a cost of U plus another cost into U plus W, right? And W is time varying, and I don't know it. it's a disturbance, right? But then what am I doing, right? Let me just skip some details. What am I doing? I have a cost function, again, in the perturbation limit. I have a cost function, maybe I'll call it E because I like an energy, which depends upon U, but it also depends upon W. It's the cost of U, a quadratic cost in U, and then maybe I still use quadratic, for example, but in U and W. Okay. So then what are you going to do? Well, if you are unable to guess that I was going to use a gradient flow, then you have not been listening to me for the last 3 days, right? Because I have been speaking about gradients constantly. Why don't you just define a controller, which is a dynamical plant? So you're trying to optimize U while the plant is moving around. And you just use the gradient descent. It's minus the gradient of the energy. Because I am silly, I put the U as a subscript of E, but I really meant it for it to be as a subscript of the gradient. So if the gradient with respect to U, sorry, so this is a typo, right? U is supposed to, the gradient with respect to U of E. So you can also calculate it if you want flat out. You can get that it is the gradient of the first piece plus the gradient of the second piece. And well, okay, you do the gradient of the second piece, you get that thing that I just highlighted. But by the way, there's also this pesky thing that gradients behave like row vectors. So we always just define the gradient as a column vector, but gradients are row vectors, the elements of the dual space. And if you do the gradient of a function psi that depends upon, for example, that depends upon y sub u, the reason you get y sub u on the left with a transpose, because you may say, Francesco, you're taking the gradient of psi with respect to u. Shouldn't it just be the gradient of psi times y sub u, right? If you do the product rule, you say, and if it's a function, it's a composite function, you do the gradient of the first times the gradient of the second. Why does the gradient of the second appear first? So I'll let you think about it. You don't need to understand anything about contraction to do this. But my point is that really the vector of partial derivatives is to be thought as a covector that lives on the dual space. And then because you transpose it, then the matrix shows up first. Okay, fine. Mystery resolved. But now, let us make an assumption. And the assumption is that I need to have a contracting system. To have the gradient to be contracting, it's the same as asking that the function E, function of U, is strongly convex. Now, if you look at it for a second, the function E depends upon U in 2 places. But then it depends upon this Y of U. I'm not sure that this is all full rank in general. If this is an invertible matrix, then I could make this function strongly convex. But you know what? If you make the first function strongly convex and the second convex, then the sum of a strongly convex with the convex composed with the linear operation is still remains strongly convex. So this is a little story about what happens when you map. Anyway, don't worry, it's not important. The point is that I'm going to assume that phi is strongly convex, and I will assume that psi is just convex. That means that my contractivity rate for the gradient controller is at least the convexity parameter for U, probably even more. And then I need to compute, what do I need to compute? Well, really not surprising. You need to compute the Lipschitz constant of this gradient with respect to W. That's, there, right? That's the Lipschitz constant with which the exogenous signal affects the state. And so, okay, you roll up you don't even roll up your sleeves. Come on, it's not that difficult. The W does not appear here. It appears only there. What is the Lipschitz constant of this? It's going to be the induced norm of that, the Lipschitz constant of this, the induced norm of that matrix multiplied together. So that's all there is to it. And so this is the Lipschitz constant with respect to W. It's the product of an induced norm, another induced norm, and the Lipschitz constant of the and that's it. And then because of the L over C squared theorem, that your gradient controller will be tracking the optimal control signal with an error of size L over C squared times how quick does my disturbance change. If the disturbance changes quickly, then I'll track with some error, right? Sandro.
What was the question? Because I wanted to ask before, because you could also analyze the performance using the cost instead of between how close you are.
Right.
In this case, it would be more interesting to understand that
Not only that I haven't had the time to write it down, but I believe I'll be able to do that. Yeah, I should add this. That's a very good suggestion. When you come back from the break, we will talk a little bit about projected and proximal gradients, which help you handle constraints in the control signal. So I will see you this afternoon. Thank you and bye.